Hello, I'm Jason. Welcome to this lesson of the AC Analysis Tutor. What we're going to do now is pick it up from the last section. We had a general overview of what alternating current is. We said that alternating current literally comes out and in, and then out the other way, back in, and it literally switches direction so many times per second. For a wall socket, it's 60 hertz or 60 times per second, but we're going to study in our circuits many different frequencies, and so all of the techniques that we're going to use is applicable to any problem that you have. But before you go any further, I want to give a little bit of review of trigonometry. Not a long review. I think you really need to have some skills from back then, but I do want to take a few seconds to show you something because it is going to tie in. So let's look at the plot of sine of theta, right? Theta, remember, is just an angle. So you can represent angles in degrees, 360 degrees in a circle, right? You can also express an angle in radians. There are 2 pi radians in a circle, right? So it's a conversion factor. 360 degrees in a circle, 2 pi radians also in a circle. So here is sine of theta plotted against theta. Now, I'm not going to be exact with this. The point of this is not to be exact here. But what I want to do is just kind of show you what it generally looks like, because you kind of need to have this in your head a little bit. I think it's helpful. Sine functions, just plain sines, sine waves, however you want to look at it, pretty much look like this. They start at the origin. That's where it starts. It goes up and then down, and then up, and then down, and then up, and then down. Notice my little marks. I'm trying to evenly space them out. That's a pretty decent looking sine there. And the thing that you need to remember, a couple things I want you to remember, is that it starts at the origin. So the starting point starts at the origin, and it goes up to +1, and this goes to -1. So that's what a sine looks like. Now, what are we plotting against? We're plotting against angles. So all you're doing is you're putting an angle in here. In circuit analysis, believe it or not, you deal with degrees sometimes and you deal with radians other times. So it's important that you have some familiarity with degrees and radians. I already talked about that a little bit. Basically, you're plotting the angle in here and you're getting the sine function as a result of that angle. So it goes up, it goes through 0, it goes to negative, goes through 0, and you can see it's cyclic. It just keeps kind of doing the same thing over and over and over again forever, basically. Now, if we wanted to compare that with cosine of theta, it would look similar, but there's an important difference. And the reason I want to show you this, even though you probably already know this, a lot of you guys, I want to show you this because it is going to be helpful for you later. So let me put my little marks here as best I can. I'm not trying to be too terribly exact. Cosines do not start at the origin. Cosines start right here. So if you had to do that, cosine would come down here like this, and then it would be up like that, reach a peak like that. Okay, something like that. All right, so when you look at this here, the maximum that the cosine gets to is +1, and the minimum that it gets to over here is -1. So I want you to stare at these, and remember that I'm not an artist, so they don't look exactly perfectly right, but they get the point across for what I'm trying to show. First thing is, I want you to know that both of these functions, sine and cosine, have a maximum value of 1 and a minimum value of -1. So the extent of the height of the function is always plus or minus 1 for sine and cosine. The other thing I want you to remember is that the shape of these guys look identical. If I took away the black axis, right, and just had these red things on the board, they would look the same. The shape of the waves look identical to one another, sines and cosines. So what's the difference between them? Well, the difference really is the starting point right there. Here we start at the origin, here we start at the maximum. So if you use your imagination, if I could like grab this sine, if I could just grab the red part, leave the axis alone, if I could just grab the red part and pull it this way so that the maximum here lines up here, then this would exactly equal a cosine. So if I could, let me say that again, if I could grab this sine wave here and just literally pull it over a little bit, then they would match up and overlay exactly with this. Or you can think of it another way. I could grab this cosine, because don't forget, the cosine, even though I've stopped it here, it continues on the other side of the origin as well. If I could grab this and pull it this way, like this, so that this ends up here, if you can use your imagination, then this again would look exactly like that. So why am I going through all this trouble to explain the sine and cosine? The thing is, they have the same amplitude, same height, they have the same shape. The only difference between a sine and a cosine is that they're shifted versions of one another. I'm going to say that again, because a lot of people when they study trig, they just learn that sine and cosine is a button on the calculator. And it is a button on the calculator, but fundamentally they are the same thing, the exact same thing. They're just shifted versions of each other, okay? I'm not going to talk much more about that here, but I just need you to believe me there that they're shifted versions of one another. The reason I'm telling you this is because we said that when we're doing alternating current, we're going to be exclusively really studying sinusoidal stuff. Sinusoids meaning I'm going to have a voltage source that's going to look like a sinusoid, and I want to see what's the current and the voltage in the circuit. I'm going to have a sinusoidal current, and I'm going to want to calculate something else in the circuit. And what we're going to find is if the circuit is driven by a sinusoid, then all the other stuff in the circuit, all the voltages and the currents everywhere else, they're also behaving like sinusoids. They may be shifted with respect to one another, but they're all going to look like sinusoids. They may have different heights and stuff, but they're going to have the same overall basic shape. But whenever we're trying to figure out how to write these things down mathematically, we got to figure out, do we want to represent our voltages as sines or as cosines? Because they really are the same thing. And in almost every electrical engineering text, we're going to use the cosine function to represent and write down all of our voltages, currents, and everything else. So keep that in mind. We're going to use the cosine function to represent voltages and currents throughout our circuit, but it's really no different than using sine. The math would look a little different because they are very similar except for the shift between them. Just kind of keep that in mind. So if you ever wonder, why are we using cosines instead of sines, there's no real reason. It's just we do that by convention. All right, so we choose a cosine function. If we had chosen a sine function to represent our voltage, it would look very similar. It'd be a shifted version. But let me show you what a voltage would look like in terms of mathematical. We've drawn it, that's a cosine over there, but let's write it down. So you might have a voltage that's V of t. Notice that voltage is now a function of time because it's changing with time. It might look something like this. Capital V sub m cosine omega, I'll talk about that in a minute, t plus phi. All right, this is what a typical voltage is going to look like in electrical engineering. It carries all the information to describe what the sinusoid looks like. So think about the things you need to know. When you're building a circuit or you're analyzing a circuit that's AC, you're going to want to know how tall is that sine wave. If you're talking about the source, I'm talking about the voltage source that's driving the circuit. You might want to know how tall that thing is, the amplitude. We'll talk about that in a minute, and that's represented up here. You might want to know the frequency. How fast is it oscillating back and forth? We'd say that the wall socket's 60 hertz, but our circuit may be 500 hertz or 1,000 hertz or something like this. And we also have something called a phase angle we'll talk about a little bit later. So let's analyze this and just see what the parts of this really looks like, see if we can make some sense of it. The number is called Vm, V maximum, that sits out in front of the cosine. That is called the amplitude. Right? That's the amplitude. This is the height of the signal, the height of the cosine. This guy is, of course, cosine, and this varies between plus and minus 1 because the cosine only goes plus and minus 1. Remember that. This guy is called the angular frequency. I'll explain why in a minute, but basically it's we talk about 60 hertz, that's 60 times per second. This is basically very, very closely related to hertz, and I'll explain what it is in just a second. But basically it's the frequency of your cosine. It's telling you how fast is it oscillating, how many times per second you can kind of gather by looking at this and converting it to regular old frequency. Don't worry too much about what it says angular frequency. I'll explain that a little bit later. This last part is called the phase angle. And the phase angle I kind of actually introduced to you a minute ago without you realizing it. You can take these functions and shift them around left and right. And so the phase angle is telling you where you start measuring from, basically. And I'll draw you a picture and show you that in just a minute. But every part of this is equally important to characterize what our voltage source looks like. The cosine, it gives you the shape, it's sinusoid. right? It varies between plus or minus 1. So this entire thing inside of the cosine just basically governs how the cosine is going to look. The frequency here is how fast it's oscillating. The phase angle is telling us how we're dragging it left and right, right? And the Vm on the outside, because remember the cosine only goes between plus or minus 1, whatever number's out here is going to govern the actual amplitude. Maybe it's a 50 volt source. That means 50 would be out in front. And the cosine is making it dive up and down between plus or minus 50 because this goes between plus or minus 1. If this were 50, that would be driving the overall amplitude. But enough of that. A picture is worth 1,000 words, and so we're going to draw a picture here to try to illustrate what we're talking about here. So here is a plot of time in seconds, like this, seconds. And then we're going to have volts up here. We want to basically plot the function that we have put on the board here and see if we can get some information out of it. First of all, this is a cosine, right? Cosines start at the top, and I'm not going to draw it too perfectly, but basically cosines look like this. And they just go on and on and on forever. Equally spaced crossings, equally spaced peaks and troughs, and so on. Now, when we're looking at just the raw cosine function, we said it varies between plus or minus 1, but we have a coefficient out in front of it. And so that means that this varies between Vm and, over here, minus Vm. So positive and negative Vm. So what we have here, this is called the amplitude. Amplitude, when you think of the word amplitude, it means maybe the strength of something or the height of something. That's what amplitude means. High amplitude means something that's tall, maybe, something like that, or something that's loud. Well, here it means the height of your source. And now I'm talking about volt. I'm treating this as if it were a voltage source, and all the DC analysis is just a steady 5 volt. It's boring. Now everything's going to be changing with a cosine, right? The height of that guy, whether it's 5 volts or 10 volts or 95 volts or 1,000 volts, is going to be governed by this number out in front called the amplitude. That's what that is. All right. And the other thing here, when you look here, you can see where the signal here, I should say the source, you can see where it starts to repeat. If you look here, between this point and this point right here, notice everything starts over. Here you go from here to the bottom, everything starts over. So this is called one complete cycle or one complete period. So what we have is t is equal to the period, and that means you repeat. Right? You repeat. All right, so I want to write a few things down underneath here that we're going to be drawing upon as we learn about this stuff. And the first one is, so let me kind of draw like a little divider line here. First thing we want to talk about is the frequency. All right, when you look at the word frequency, it means how much does something oscillate. That's what the word frequency means. In electrical engineering, the frequency is 1 over the period. So when you talk about the period of this guy, the period is going to be in seconds. So you may plot this and I may say, hey, the period of this wave is half a second. That basically means that it starts to repeat itself after half a second. That's called the period. If I take 1 over the period, then I'm going to end up with another unit called hertz, which means cycles per second. How many times does the thing do complete oscillation in 1 single second? So this F here, this is the 60 hertz that we're talking about in the wall socket. That's the F. That's the frequency or the amount of cycles per second there. So the unit here for frequency is hertz, which is cycles per second. How many cycles per second is this wave doing? Now notice that we did not use this frequency up here. We used something different called omega. It's like a little W here, and I called it an angular frequency, and I told you, yeah, it's kind of a frequency, but it's a little different. I'll explain later. Well, now I'm going to explain it to you. What we have here is, I'll write it down here, angular frequency, right? Omega is directly related to the regular frequency by 2 times pi times f. In fact, this I want you to remember. I don't tell you to memorize too many things in any of my classes, but one of them is this. Omega is 2 pi f. 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 I want you to say it because you're going to need to convert back and forth a lot. You need to remember that omega is 2 pi f. Right? Now, what would the units of this be? Since this is cycles per second, and here we have kind of an angle in radians, 2 pi radians in a circle, what you get here, I'll go ahead and use the red here, the units is radians per second. That is the unit of angular frequency. All right? So I want to take just a second to kind of make sure everybody understands that. Okay? I want to make sure everybody understands that. When we talk about things that repeat, okay, there's kind of two ways, and especially in terms of sinusoids, there's two ways to look at it. One is to go figure out the frequency. That's how many cycles per second the thing is changing. And the other is to talk about the angular frequency, which is how many radians per second the thing is changing, right? They both kind of mean the same thing. If you have a higher frequency, it's changing faster. If you have a higher angular frequency, the thing is changing faster. In fact, they're actually related directly by just a constant here. So really f and omega are really the same thing. They're just related by a constant. So why do we even do that? Why don't we just deal with frequency? Because that's the one that makes sense to me. When you first study this stuff, you're like, frequency, that's something I can wrap my brain around. Why are we talking about radians and angular frequency? And the reason is because if you look inside of the cosine function, we have the frequency times time plus some phase angle here. All right, this is the angular frequency times time. Don't forget, whenever we take the cosine of something on your calculator, let's say, you're always taking the cosine of an angle, okay? You're not taking the cosine of cycles per second. You're not taking the cosine of inches. You're not taking the cosine of cubic centimeters. You're always, for it to make sense, taking the cosine of an angle, which is, let's say, radians, because radian measure in math is what we typically use in engineering, radians, right? So at the end of the day, whatever is inside of this guy has got to be an angle, and it typically needs to be in radian measure, right? So if we just put f here for frequency, then that's cycles per second, and then we'd be multiplying times time, which is seconds. So then what we end up getting there is cycles. So we'd be taking the cosine of cycles. That makes no physical sense. We have to take the cosine of radians, right? So we introduce this thing called the angular frequency. We say it's directly related to the regular frequency. So instead of talking about how many cycles, we're going to talk about how many radians per second the thing makes in one single second. So if you take radians per second, which is this unit, and you multiply by seconds, then you just get radians here. So this product gives you radians. This is just an angle, so you just have radians in there, and then you can take the cosine of it. That's one way to look at it in terms of units. Basically, you have to have radians somewhere in there to take cosine of it, and so we're going to be dealing with omega all the time, which is radians per second. The other way to look at it is it's just another way of representing cycles per second. Here, if we want to know how many cycles per second, we just look at the graph, look at 1 second and count how many cycles we have, and so on. But when we multiply by 2 pi, what we're doing is, think about the unit circle from trigonometry. That's why I said probably a good idea to review some trig. Think about the unit circle. There are 2 pi radians in one full revolution. So here we're talking about kind of like one full cycle of this wave, but instead of thinking about the wave, think about it going through the unit circle one time. That's one full revolution. That's 2 pi radians. Every time we go around, 2 more pi radians, 2 more pi radians. So I can express anything cyclic, especially in terms of cosines. I can express how many times is it going to go around the unit circle in 1 second. How many integer multiples of 2 pi is it going to go all the way around per second? And that ends up boiling down to being radians per second. So when you take the frequency, multiply by 2 pi, what you're getting is you're basically figuring out how many times does this thing take a full trip around the unit circle of 2 pi, which would be radians per second. So there's a couple different ways to look at it. I'm trying to give you a little bit of a solid foundation there, because sometimes you look at it and you're like, why are we using omega? Why are we multiplying by 2 pi? It's just another way of representing a cyclic term, right? So instead of saying we're changing, looking at the sinusoid as it goes around, and we're counting how many cycles per second, we multiply by 2 pi, that's how many radians, how many 2 pi times we go around the unit circle per second. All right, now the next thing we want to do, I think we beat angular frequency into the ground, is amplitude. And amplitude, we already talked about, fundamentally that means the height. the height, which is V sub m, right? That's the height of this guy. If this were 36, then the amplitude would be 36 volts. And by the way, amplitude is measured from the top to the axis here. It's not measured from peak to peak like this. So if this were 36, from here to here it would be 36 volts. If this were 150, it'd be 150 volts. Basically, whatever number sits in front of the cosine is the amplitude, which tells you the height. And then we've already talked about it, but I'm going to write it down again. The period is called T, which is the length of time for one oscillation. So I have some more stuff to talk about here related to this, but I want to stop this lesson here, let you absorb this. In the next lesson, we're going to talk about what we call this phase angle here. I want to draw some more pictures and show you what that means. But as a really, really quick recap, just kind of keep in mind that every single voltage or current that we talk about in this class is basically going to look like what we've written up here. So you have to have something to go in each one of these spots. Whatever number you put out here is going to be the amplitude. So if it's voltage, then this will be the amplitude of the voltage that we're talking about. If this is a current source or something, or a measuring current, the number out here is the amplitude of the current. It's the height of this wave. Its cosine, that basically tells you the shape of the thing. Inside here we have frequency, but it's not expressed as just how many times per second. It's expressed as angular frequency. How many radians per second is it going around? Keep in mind that 2 pi radians is 1 time around the unit circle. So this is radians per second. When you multiply by time, you end up with a unit of radians, which matches with what we need. And then we have the phase angle here, which is going to shift it left and right. So what I like to do is close it down now, make sure you understand this, and we'll do some examples and solidify it a little bit later. Follow me on to the next section. We'll talk about the phase angle in terms of alternating current circuits.